Hello everybody, welcome back to my YouTube channel. Today we are going to look at a really special paper on how to use machine learning for chemistry. In this case, we are looking at a paper called Self-Feedback Knowledge Elicitation Approach for Chemical Reaction Predictions. Now, as you all know, right, what is a chemical reaction? It's essentially taking something like two reactants and predicting what would be the product right out of that reaction, and now predicting such a chemical reaction and its output is a very difficult challenge, right? And it often involves a lot of quantum mechanical calculations, which is expensive, right? And which takes quite some time, right? But what if we can predict it directly using machine learning, right? And in this case, it's a bit more specific, right? So, okay, let's read through the abstract together. Okay. The task of chemical reaction predictions is important in advancing drug discovery and material science, but its effectiveness is constrained, it's hindered by the vast and uncertain chemical reaction space and challenges in capturing reaction selectivity, particularly due to the existing method's limitations in exploiting the data's inherent knowledge. So when you do a chemical reaction, right, there's a lot of ways that it can go, and it's kind of hard to predict where it could go, right? So okay, what they propose here is a data-curated self-feedback knowledge elicitation approach. So it starts off with iterative optimization of molecular representations at first, which means understanding the molecule from the deep neural networks perspective, and then try to extract the knowledge on different types of chemical reaction in which they call this RTs. Then they use adaptive problem learning to infuse the prior knowledge, right, into a large language model, right? And by doing so, they managed to achieve a lot of improvements, right? About 14% of accuracy in predicting retrosynthesis, right? And not only that, but also 74% increase in reagent prediction accuracy, right? And not to mention, but it is also able to handle multiple task chemical reactions as well. Now, this is a really cool showcase of how LLMs can be applied in real world applications, right? I mean, at least in scientific applications. So let's go through, right? Let's go through let's go through the conclusion and see if it offers any more details, any more general details there. Okay, let's see. Okay, found it. Okay, so in this study, they can reconceptualize the task at hand as SLM. Not so sure what SLM means, right? A small language model, probably not. But okay, and they pioneer a data-curated self-feedback knowledge elicitation method to identify knowledge partners, specifically RTs. They then use dynamic problem learning to integrate this prior knowledge into LLMs to enhance the accuracy in CRPs and multiple task CRPs. Okay, what does CRP means? Chemical reaction prediction, I think? Not so sure. Okay, this research is blah blah blah. It's groundbreaking. Okay, sure, why not? Okay, and now let's take a look at okay, so let's take a look at the introduction just a bit, right? So okay, CRPS chemical reaction prediction, just like I mentioned, and RTS reaction type. Okay, got it. So okay, okay. The application of chemical reaction prediction is fascinating, right? Drug discovery, drug design, material discovery, you name it. There's a lot of ways, right? And with AI, it's gonna make it much better, right? That's the idea. Now, to talk about, oh yeah, how about Chat GPT, GPT-4, all of these things, and it also stated, oh yeah, there's like scientific language models, something like Galactica. I don't know if you still remember about Galactica, but it's a large language model that was previously released by the AI team from Facebook, but it's now called Meta for some reason, right? And obviously, there are a bunch of these models like MoT5 and BioT5, as well as things like Instruct Mode that also does chemical reaction prediction, right? But and they say most of these large models are not interpretable enough, and it requires a lot of training data, and it's something that we clearly lack in the scientific community is those juicy, large-scale training data that we often see in vision models training. So okay, right. Prompt learning coupled with LLMs for fine-tuning is the standard approach, right? And to say, however, the static template prompts can lead to rigid guiding patterns in LLMs, potentially impacting their accuracy in general. Dynamic prompts, okay, and to say dynamic prompts can be better than static prompts, right? With the injection of prior knowledge into LLMs. In chemical reaction prediction, identifying the types of reactions can narrow down the chemical space that needs to be explored. So imagine if you have the entire chemical space of this size, if you know what kind of reaction it's going to be, you can then reduce the space into a smaller subspace which you can then explore around, right? So the chances of you finding the right reaction pathway is going to be more plausible, right? So, okay. However, the data sets typically lack reaction type labels, including only reactants and products. True. While too few categories in annotation methods limit their effectiveness, too many can reduce annotation accuracy. Okay, too many categories can be bad too. So, okay, the synergistic effect of multitask cooperative learning, treating chemical reactions as a unified domain of molecular knowledge, has yet to be fully leveraged. Therefore, they propose these few key issues here. Number one, how can we balance annotation accuracy and number of reaction types in knowledge elicitation by large language models? And number two, can LLMs perform better through prompt-based knowledge infusion? Right? They call it knowledge infusion, but it's just really input. Anyway, step three: can a multitask collaborative approach improve the performance of LLMs? All of these questions will be much clearer as we go through the paper, I believe. So, all right. So blah 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 blah. Okay, so the task can be okay. So the task of chemical reaction prediction can be broken down into predicting the right reaction type and generating the correct molecule as the output, right? So okay, right. And they say their approach would work the best, right? But we shall see, right? Okay, and I mentioned dynamic prompting. We introduced dynamic prompting, which then increases by 10% in adaptability for knowledge injection into LLMs. And then talk about, oh yeah, by injecting prior knowledge, they can have an improvement of 14.9% across reaction prediction tasks, but we shall see if that's true or not, right? So right here they have a diagram from what I can tell. Okay, right. So they show, okay, these are the prediction tasks usually, right? So okay, a forward read, okay, for those people who are not a major in chemistry, right? So there's like different type of predictions that you can make typically when you're trying to synthesize a molecule. Is that first of all you need to know, right? Okay, what kind of reaction is this, right? It yeah, what kind of product is going to come out when you react these three different reagents to together, right? So yeah, and the other one is, given a product, can you guess the possible reactants, right? And the third one, which is, okay, given a few of the reagents, right, and the final product, can you guess the missing reagent that's required in this case? Yeah. So it's kind of like filling in the blanks, right? But for something like retrosynthesis, it can go multiple different ways, which I would like to see how they handle that. Okay. Okay. And part B, current large language model methods for chemical reaction prediction. So in this case, we give it a prompt. Please suggest possible reactants for the given product, and this is the product. Yeah, that's the product, and the LLM should produce some kind of suggestions to it. In this case, it's invalid, right? But using their self-feedback knowledge elicitation for enhancing chemical reaction prediction, their approach, it seems to give the correct answer, right? So hold on just a second. Okay, sorry about the interruption. Let's get right back into it. So self-feedback knowledge elicitation for enhancing chemical reaction prediction. So right here, as what I can tell from this figure here, it seems like okay, so they have the input. Okay, I assume it's the input reagents and the output product, I think, and it goes through an LLM, which then they extract some knowledge patterns out of that, and they curate the reaction type from the knowledge patterns, right? And they do some kind of a accuracy refinement, which is some kind of a self-feedback to evaluate whether or not the annotation is correct in the first place. If it isn't correct, it will inform the LM to make corrections to it. And that's the strategy that they go to. So on the right, they have the instruction templates, which is basically just some prompts. Okay, it states forward reaction. Number one, please suggest. Number two, given these products, can you propose the corresponding reactants, and so on and so forth. And retrosynthesis and reagent. And there's some kind of an adaptive selector. Mm, not so sure what it does exactly, just by looking at the figure. And then it leads to this prompt right here, giving this products, can you propose the corresponding reactants? The reaction type is blah, right? And the input of the molecule is right here, right? And then the LM would produce a prediction about what kind of reagents would be suitable to make this product right here. In fact, this is a esterification reaction between salicylic acid and acetate anhydride. Okay, now let's look at the caption here. Okay, these are the overviews. Okay, so right here, okay, current LLMs for chemical reaction predictions, right? They have indicating rational predictions but lacking in reactive validity. So basically, their rationale, their thought process are usually correct, but their final outcome is not, as far as I can tell. So in their approach, the self-feedback approach, okay, they demonstrate the enhancement of chemical reaction prediction through refinement of knowledge patterns, notably reaction types, using a self-feedback knowledge elicitation technique. This knowledge elicitation serves as a way to curate data for knowledge distillation. Okay, so they perform some kind of a knowledge distillation at the end of the day, where the reaction type is integrated into the large language models using adaptive prompt learning, facilitating the planning of reaction pathways in CRPs. Okay, this is not exactly clear what they're doing, and the figures are not too helpful. So what I'm going to do right now is probably just go through some, just go through their methods. Right? Okay, so let's go through their methods right now. Okay, so in this methods section, they were talking about their approach. Right, so let's start off with an overview. Okay, so first they will introduce the foundational data structure and how they prepare it, and next they will go into the self-feedback mechanism process. Okay, and finally they will say how they train their LLM on specific reaction prediction tasks. So this approach does in fact need to fine-tune their LLM on their own custom data set. So it's not entirely cheap right here, but that's okay. Okay, let's see how long is it. Okay, I see. Right, so it's around 1, 2, 3, 4, 5. Okay, right. So let's go through it step by step in order to fully understand their approach. Okay, the approach depicted in figure 2, right? In figure 2, let's just read for now. On focus to three-stage training strategy. Firstly, they divide the dataset into training, validation, and tests, with a focus on knowledge extraction to annotate for reaction types. This stage involves refining the selection of the optimal clustering approach in training the LLM RT, leading to the formation of the self-feedback clustering mechanism. Right. In the data curation phase, the frozen LLM uses prompts along with its inputs to perform reaction type annotation on validation test set. And finally, the method uses the enhanced prompt for fine-tuning the LLM. Okay, so if I were to understand this, so what this probably is something like, okay, so it starts out, okay, so let's say D is the training set, so we split it out into T, V, and T, train, validation, and testing. Okay, the stage, okay, then we refine the selection of optimal clustering approach and train the LLM. Right. Okay, right. Okay, so it would provide something like, okay, right. So at the end of the day, all we really want is the enhanced prompt so that we can fine tune the LLM. Okay, so, and the task can be described, I think, which we already done. Okay, we are concerned about forward reaction prediction, record synthesis prediction, and reagent prediction, right? Which I already talked about previously. And they say that, okay, right, we can generalize all of these problems into this single statement, mathematical statement right here. So F general, taking a set of the reagents and the product that, and it will give you the predicted reactants, products, and reagents, right, for any given chemical reaction. So this is a very general statement right here. So okay, and then define the knowledge-driven prompt, denoted as enhanced prompt, a combination of adaptive instructions and knowledge priors RT, which is defined right here. I don't know why the A is before the I, but that's whatever. Okay, incorporating prior knowledge by enhanced prompt enhances the specificity and accuracy of these predictions, which then modifies the general function into this. So if we add in the enhanced prompt, right, which contains prior knowledge, it becomes that, which is basically just adding a new term after P, the product term, right? So yeah, so that's that. Okay, right. Mm, 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 mm. It addresses the scarcity of reaction type information in real-world data sets, and the dynamic prompts prevent rigid guiding in LLMs, offering a solution to enhance prediction accuracy. Okay. Let me see, what else more do we have here? Okay, and they have the data processing pipeline here. Okay, in the study, they use molecule-oriented instructions from a dataset that contains three chemical reaction tasks. So they prepared the dataset by converting the input into smiles, obviously, right? And yeah, and the dataset's instruction components are sorted by different task types and integrated into their instruction template library, aiding the infusion of blah 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 domain-specific knowledge into the models. Okay, and now here's the meat of it, right? So okay, data pre-processing. So they make everything into smiles, right? And they clean all those entries that cannot be converted into smiles, okay? And yeah, and they split their data set into a ratio of this. Wow, what the heck? 98% for the training and 2% for the validation in the test set. Oh boy, I didn't expect that, but okay. All right. Section 3.3, knowledge extraction and data curation. Right. This subsection explains the process of self-feedback knowledge, elicitation in reaction prediction problems. Okay, and then talk about their approach. So obviously we have to go through the approach. Let's see, they have their pseudocode there. That what we should do. Let's try to understand their pseudocode. So okay, initialize the LLM model for encoding methods, set the cluster method and number of range, prepare the instruction templates library. Right. So they do a loop, a main loop over the encodings, and then they do a sub loop from number 3 to 12, such that they set the cluster number to that, and that. Right. From okay. So let me get this straight. So the clustering is an attempt to like get the reaction type label, sort of. It's like, yeah, be okay, if we have like a proper data set, right, we can obviously see that clusters of reactions, right? If there are clusters of reactions, they are most likely going to be like a specific type of reaction that's like unique compared to other clusters. Okay, right. If that's the case, that means they are performing clustering in order to get that reaction type label indirectly, which is pretty smart. Um, okay, and then do those clustering and then get the and then evaluate how accurate their annotation are. So let's say perform clustering, annotate with identify RTs and that. Hmm. Yeah, I mean, I don't fully understand the entire paper that well, just yet, because this is my first time reading this paper, but it seems to be quite interesting, right? Because this isn't usually the type of paper that I would read, but it has to do with my work, 10% maybe, yeah. But it is interesting to learn new things like this one right here. Yeah. Okay. Yeah. Let me see. But unfortunately, I don't have much time for this paper. Okay. Adaptive knowledge. Okay. Right. How about if we go through this? Adaptive knowledge injection. So, okay, it can views. Yeah. So please suggest. Please provide. Okay. Right. Right. So what they meant by adaptive knowledge injection is that their prompt keeps on changing, uh, de- depending on the input sample. Is it? Because like if you take a look at here, right, the sentences are essentially asking about the same thing. Like yeah, yeah, they are all asking about like okay, what's the product given these reactants and reagents, right? And those are just different ways to phrase it, and you don't actually know what kind of prompt is which one of the sentences are the most is the most effective um, for boosting up your prediction accuracy, right? So that's that. All right. So they introduced an adaptive selector. So I'm assuming the adaptive selector is kind of like helping this hyperparameter selection. Um, it acts like a hyperparameter selection algorithm, but just for the prompts, I believe. So during that. Okay, so the adaptive selector then evaluates adaptability through vector differences between the input embedding and each template embedding. Okay, right. Yeah, maybe I have misunderstood it. For each batch, this process entails matching a single input with multiple instructions to determine the best fit based on adaptability scores. Okay, right. So there is some kind of a cosine similarity here, is it? Um, but crap, not so sure what it meant. Yeah, and also, why do you even care about like highest adaptability in this case? Hmm. Okay, and that's the equation right there, trying to measure how close they are with respect to the input embedding. Okay, similarity score. Okay, the higher relevance when the value is larger. Okay, I would assume that having higher relevance would boost the accuracy prediction. Sorry, I mean the prediction accuracy. Not entirely sure either. Yeah, I guess that's that. Yeah. So okay, right, right. Yeah. So how about if we take a look at the results now? Because yeah, and this is the clustering result. Let's see. Yeah, so you specify too many clusters. Wait, hold on. Cluster number something right here. Hold on, sorry. Uh, hours. Okay, right. So for prediction, it looks like this one is that. Hmm. Right, so it looks like their approach does improve it by a bit, right? 99.3%, which is better. Uh, but some of them are pretty minute. Okay, and this one is better than their approach. All right, as for retrosynthesis, yeah, it's better in all places, though, and again, some are pretty minute, but some are more significant, right? Especially for stuff like exact match, this is pretty tough to to uh, to improve on. It's a pretty tough metric there. Mm, yeah, yeah. Obviously, right. If you want to get the exact match, you need to get like 100% accurate for the smalls comparison, right? Which is something that's gonna be pretty hard to do, but it seems like their approach works well, right? And if we take a look at here, the multitask performance summary, it improves by 14.9%. So yeah, let's see. Okay, let's go through the discussion right now. Okay, they've highlighted their approach to annotate reaction type as a solution for as a way to solve the data's scarcity in real world scenarios. Their approach shows that LLMs can do a lot of internalization thinking process to predict those things. And okay, right. They also talk about how significant annotating for reaction types are. So, okay, right. And then they mention here the model performance can be improved with higher cluster numbers, but this introduces challenges with annotation accuracy. Thus, finding a balance between annotation accuracy and quantity of n, the number of clusters, right, is important, right? Because yeah, yeah, if you want to like find like a how do I say, right? Because the overall bottleneck that prevents the accuracy from going up is obviously the ability for us to like make precise clustering decisions, right? Using the algorithms that we have. So if you cluster it too much, right, then it's more probable that the cluster that you make is not actually the actual like correct cluster that it's supposed to be in the real world, right? So so in that sense, kind of um, uh, it kind of flows with the logic here. So the logic kind of flows. So okay, knowledge learning in LLMs. Yep. So if you have the feedback mechanism, it should work quite well. Um, okay. So okay, and there's the future work. Uh, yeah. So the future work. If you're interested, you can have a look into that. But it's more just about like how you can like further improve their adaptive algorithms, and then I would also say even some of those clustering techniques, maybe those can be improved as well. Yeah, but yeah, overall, I say it's a pretty solid paper. But yeah, but if if you're not someone from this field, right, it can be a bit confusing even to me, because my research area is mostly on like predicting the molecular properties, but not necessarily predicting the reaction types. And yeah, this is my first time reading this sort of paper, so yeah, you will have to forgive me about that. But yeah, yeah. But I hope you and I learned a lot from this paper to, together. And yeah, if you like this video, make sure to like, comment, and subscribe. And I will see you guys in the next time. Bye.